And that's the concept behind the Hall effect. The book goes into math, but that's as far as I want to take this right now. And I say, let's take a break. I'll come back. I need to get a couple of props. And no matter what I get, I'm sure I'm going to forget something. All right, so I'm going to put a pause on the recording here on Zoom and on the other one. And we'll be back.
Please tell me that was a recording.
That is awesome.
One more time.
I don't think you know this is funny.
I didn't hear it, so.
Wait, that's
Now,
okay.
I'll sit in it.
what's gonna happen is that we're gonna turn this on, and when it turns on, the high side is on this side, so it's gonna come along here. Current's gonna come down your left side, up the right side, and then back through. So assuming all my wires are good, we have a circuit. So the question is, what do we expect to see?
The foil trying to get away from each other at the bottom.
All right, because I'll have current flowing down one side and, actually from your point of view, down that side and up that side. I have current flowing in opposite directions.
So want to be attracted.
Well, those are our two choices.
Or
So-
repel.
For the current that's going up, current that's going up, my magnetic field is going into the board over here and out over here. For the current on the left side, current's flowing down, the magnetic field is coming out, out on the right side and in on the left side. So out over here and in over here. So where is the total magnetic field going to be the strongest?
In the middle.
Yeah, and the top.
So which way will the wires move?
Towards each other. Didn't we have one?
Well, the one we did before, the current was going in the same direction.
Oh, now they're going the opposite. I see. So then, but before they were moving towards each other, do they want to move away from each other now?
Yes, the one will move away from each other. Where the magnetic, it will go towards where the magnetic field is weaker, so which means towards the outside, or from the point of view of the L cross B. The wire over here is being bathed in the magnetic field created by the other side. The magnetic field is going out, current is going down, and so, let's see, current's going down, oh, so DL cross B, the force is in that direction. So this is going to be forced outwards, and by Newton's third law, or right-hand rule, they should go away from each other. Please work. All right, so I've done this demo many times. I went through a phase for a couple of semesters where all it did was just twitch a little bit. It was very sad. And then suddenly it started working again.
If you put a paper clip at the bottom, do you think it would help it stay like that?
I've tried putting weights down at the bottom to try to make sure it's more level, but it weighs too much.
Gotcha.
So with the sides as parallel as possible, that's the ideal right there. But first time I did this, I just had a whole string of batteries, and it sort of worked, but you had to make sure the batteries were actually touching each other. Just one small gap anywhere along the chain would mess it up. Then I started using power supplies. It worked really nicely. Then it stopped. And there was one time students were doing a lab. I might have mentioned this already. Obviously, they're supposed to buff out, and when they turned it on, they came in. Do not know why. switch the leads around there, which all that should do is just change the current from going like this to going like that, and they start going out. There was one time, it just was just doing the twitch, and I thought, hey, let's just turn this around. So I turned the aluminum foil sort of inside out, and it started working. Let's crank this up.
You defied physics.
Pardon?
You defied physics.
That's right. Well, the one where they came in, it was in the back part of the room over there, which is where the part that was over the ancient Indian burial ground. So that's so, because there's so little resistance in here, the breaker's gonna trip. So you'll hear it click when it goes, and we can just reset that. See?
Oh,
Yeah. And it works beautifully, yay.
Nice.
that was cool.
Now, to reset something like this, it's either the button on the front or back. There's a white button, it's usually the one in front. Now, the lab would be you've got a meter-long strip, you basically set it up something like this. There's a whole lot of picayune measurements, and you measure the distance between them, and then when it puffs out, you measure where it is at 5 different points, about where it is, and then do some estimates, or,
Seems like it would be hard to get.
I think it would,
that
yeah,
quickly.
hard to keep everything constant enough for the measurements to be on point.
well, if you do it enough, so. What?
Probably easier if you got one of those.
Oh, I turned it off, that's why. So you do it a couple times and you eventually start getting measurements there. All I'm doing is resetting the breaker and it's immediately tripping off.
So it's tripping because it's detecting an imbalance between the positive and negative side?
It's tripping because there's a limit to how much current that this will take.
Okay.
And we're exceeding that current because the resistance is so tiny.
So low, yeah, okay.
So in the lab, you figure out, for example, what the resistance is 3 different ways. You figure out the current 3 different ways. You figure out the voltage 3 different ways. You figure out the thickness 3 different ways. And you take what you think is the correct value to be using. You do your calculations at the end, and then the last question is there a different combination that would get you better results? And then that comes down to what I think is the fun part, but at this point, I've got a spreadsheet set up that just does a brute force, so I just type in all the information, it calculates the best results. So anyway, evidence that what I'm sort of talking to you about is not complete BS,
Thank you for the demonstration.
and it worked, yay.
So we're doing this next class?
Pardon?
We're doing this next class?
No, we're not doing this lab next class.
We're not doing the lab at all, right?
No,
So this was for funsies.
yeah.
So he was trying to explain.
I might change my mind, but right now I'm leaning towards a different lab on Wednesday.
He was trying to explain why he didn't want to do it, because that is
It-
like inconsistent.
The trouble is that I'm not convinced yet that for people who get percent errors under, say, 10%, whether that is just a random occurrence or they did a really good job. So there's a certain element of luck that seems to be involved in it. That's the part that makes me wary.
Percent errors in
It's the best
general,
way to
or
make
just
it
for
good.
this lab specifically?
For this lab,
Oh, students get like.
in general, percent error, percent difference, not percent error. Percent difference ranges usually from a couple of percent to 200%.
Oh, this lab's like really inconsistent.
Range.
Pardon?
In comparison to the other labs, this one's like really inconsistent.
Yes, yeah. But I still like the lab, because to me, that's really cool that it does that.
It is.
Cool.
Random question.
So if we had the currents going down, where do they stick together?
If the current were going in the same direction, they would be attracted towards each other. So we would need actually,
Do it. You have the science.
I mean, if you put your finger there, it doesn't.
You know, like, if you do like a Mobius strip, won't that do it?
I don't get it.
I think so.
Oh, okay.
Because the current doesn't really care which way it's flipped.
Yeah, I'm realizing that now.
Alright, so that's that. So if I had this. Let's see, I need this one attached to this one. This might weigh it down too much. I don't know. I have not done this before.
Does it need to be held?
Let's go to say no. Just because this particular power supply gives more power than most of them do.
It's an infinitesimal amount of voltage, you're not gonna feel very much.
I don't know if I'm trying to be part of the circuits data.
No. I got a something if you want.
As long as you're standing on two.
Yeah, I'm just
Two touch
not feeling confident on this one.
Thought of a good pickup line.
Oh yeah, all the good markers on the right side and all the
Are your
trash
parents
markers are on the left
retarded?
side.
Is yours special?
Trash is on the right side?
Trash is on the left, but good
That's
is on
so
the right.
bad.
Would it
That
not
doesn't
be?
get him, I don't know what would, dude.
Would it not be?
Yeah, I'm gonna have to
That's so
figure that one out. 'Cause
That's
it-
so
it-
good. I don't-
I put small objects in here and it really messes it up, so, if I have this,
It's
I
good
take
and
it
terrible
down, I
at
don't
the
think
same
it's gonna
time.
be like.
Oh, okay.
It's a genuine pickup
We'll save that for another time. All right, so
Is that like the average range there?
let's flash back to Kirchhoff's junction rule.
I think they start at the belly at 15. And if you're interested already, is there anything?
All right, physics time. What is Kirchhoff's junction rule?
Whatever current goes in, goes out.
Yeah.
Yeah.
Gonna go back out.
What is the one place that we have talked about
Okay.
where current flows in but does not flow out?
The ocean.
The capacitor,
Capacitor. That's what I was going for.
I like the ocean.
Like, yeah, the Department of Public Defense class, out of all places.
Because they have.
So if I've got my power supply here and I got my parallel capacitor there, I have current flowing onto this plate. I have current flowing off that plate, but in between, there doesn't seem to be any current, which seems to violate Kirchhoff's rules. And physicists hate rules being violated, so they came a way of working around that.
Yeah, it's more rules.
I know that the electric field is equal to, between the plates, sigma over epsilon sub naught, which is Q over A epsilon sub naught. If I multiply both sides by A, actually I can multiply epsilon sub naught also, so it's an epsilon sub naught E A is equal to Q. Take a time derivative. That's a constant, so that just pops out. So that's epsilon sub naught dEA dt is equal to dQ dt. Well, what's dQ dt?
Current,
Yes. And I realized that.
Not recording.
It's recording, but just pointed in the wrong direction. So that's equal to current. And E times A, the electric field times area.
charge density.
Not charge density.
The flux,
Which kind?
the electric flux.
Yeah. So we have this current, it's not caused by a change, by charge moving, it's a current that seems to be caused by a change in the electric flux. And to differentiate it from the other type of current, This is called displacement current.
What's that little symbol right next? Oh wait, that's the derivative of electric flux over time?
What, here?
Yeah.
Yes.
Okay.
Just turn off.
Yeah. Oh, you needed it right there. I thought you were gonna be up there for a while, so I decided not saying anything.
Oh,
But,
no problem.
sorry about that.
I was looking at it with my eyes and I was hoping you would like see my gaze.
Jacob
Oh,
was
you
playing.
did?
All right, so if we look at Ampere's law has that, let's get rid of some of this. Ampere's law is that if I do a line integral of the magnetic field around some closed loop, that I get mu naught times I. But there seems to be a second kind of current here, so if we just stick in the second kind of current, so we have the current based upon charge flow and then current based upon this change in the electric flux, the formula becomes this, which is mu naught I plus distributed mu naught times epsilon sub naught, the time derivative of the electric flux with respect to time.
That's Fox, the board's about to shut down.
Or something's happening.
It's doing something.
Live.
It worked.
So what we have here is Ampere's law with Maxwell's correction. So at this point, we have three of what are generally called Maxwell's equations. We have the integral of the electric field with respect to the area. In other words, the electric flux through a surface is equal to the enclosed charge divided by epsilon sub naught. We have the magnetic flux through a closed surface is equal to 0. We have the integral of the, oops, wrong one, V dot ds is now equal to mu naught I plus, I guess, I sub enclosed or inside the loop plus mu naught epsilon sub naught by t. There seems to be some symmetry here. I've got an E dot dA and a B dot dA. I have a B dot ds. Is there an E dot ds?
Probably.
Indeed there is. And that is what we're doing next. Faraday, from which we get the unit Farad. Faraday noticed he had wire here connect to some sort of power supply. And he had another wire beside it connect to an ammeter, just measuring current. And he noticed that it starts out with no current in it, and he flips the switch so that we suddenly have a current flowing through here. He noticed that the needle would deflect and then go back to 0. When he disconnected, the needle would deflect in the other direction and then go back to 0. He played around with this long enough and eventually realized that what was actually changing here, what was causing this needle to deflect, is that a current was being induced over here. And that the voltage, the induced voltage, or I guess probably the induced EMF, is equal to, well, it turns out, the change in the magnetic flux. I'm gonna make one small change to this in just a moment. Now Faraday, as best as I can figure out, Faraday realized that there's a connection there. He didn't come up with a math equation. The guy who came up with the math equation was a guy named Lentz. And there's a negative sign there. So a couple things here. This is EMF, this is not permittivity. The negative sign is a fortunate thing, because if the negative sign did not exist, what this means is that when I connect that current there, this is going to create a change in the magnetic flux, but the current that is induced, the voltage that's created to create this current, is going to oppose the change in the magnetic flux. So if the magnetic flux increases in here, then the current is going to try to decrease the magnetic flux. If there's a magnetic flux already going through there and you disconnect, the current is going to try to bolster it up. The induced current is always going to try to reduce the change. If it did not reduce the change, think about what would happen. So I start out with it disconnected, and then I connected. I go from no magnetic flux to having a magnetic flux through here. If this current increased the magnetic flux, so the current moved in such a way that the magnetic flux increased, then that suddenly increases the magnetic flux, which would induce a current over here, which would increase the magnetic flux, which induces a current over here, which increases the magnetic flux. And you get the cycle, and you run away. Free energy, or most likely, all of mankind would have been wiped out. No free energy. That's, if you ever have one rule of thumb you have to go by in physics, it's no free energy. There's always going to be a cost somewhere. So we induce a current here, but the current is trying to minimize what's taking place. This is voltage.